Welcome back to Fat Mama Physics. This is, unfortunately, a very long video series, but we are on part 6 of your 4 big kinematics equations. In front of me, I have a free fall example in which I am going to go over completely, meaning if you would like to give it a try, this is your time to do so. So you can pause the video and give it a shot first, and then I will go over it. Okay, time to go over this one problem. We have Jamie tossed a rock upwards with a velocity of 5.4 meters per second on the edge of a 32-meter cliff. So let's start highlighting our problem. Step 1 in problem solving. Rock is thrown upwards with that particular velocity, meaning that's probably our initial at this point. That's where the rock starts from. Jamie is our person, is going to throw that all over the edge, or he is standing on the edge, and he's on a 32-meter cliff. Now, whether the rock will actually fall to the bottom of the cliff, we don't know. So I'm just going to write here an S for displacement and put a question mark down, because I think that's going to depend on what the problem is going to ask of us. So question A is asking for us the maximum height above the cliff that the rock reaches. That is specifically asking for some sort of distance, and I'm going to write here displacement because that's what it is. Now, let's do the next step, which is drawing a picture. Here we have, I'm going to draw it over here in case I need more space later. Okay, I'm not going to draw Jamie. I'm sorry, Jamie. I don't really care about you. I care about this rock here. The rock is going up, okay, and it's going to go up. It's going to reach some maximum height, and it's going to come back down, and we don't know where it's going to land yet, but we do want this maximum height at the top here. I'm going to label going up as my positive direction, and I'm going to do the rest of my labeling, which I'm using this color pen. We know here the initial velocity is 5.4 meters per second. We are trying to find this maximum height here, so that's our maximum height. And because this is free fall, we know that the acceleration is always 9.8 meters per second squared, and since I have labeled the upwards direction to be positive, this must be negative. Gravity is acting downwards. Another characteristic at the top of this trajectory at the maximum height, from what we talked about last video, the final velocity we know is 0 meters per second, and that's because we chose this point up here as our final point of destination for our motion. Initial here, final here. Next up, we need to identify the concepts involved. So here we do have acceleration, which warrants us to look at our 4 kinematics equations, which I am going to quickly jot down here. Looking at what we have, VSU and A. VSU and A, that looks like this guy over here. That's the one that we need. It has all our unknowns and our knowns. So let's write that down. If we're solving for S, it means we have to isolate for it. There's a few things that we can cancel out before we do that, such as the final velocity, this being 0. And now we just need to isolate for the S, which I'm going to move the U squared to the other side. Now we can just divide both sides by 2A to isolate for the S. Substituting our values in, we get negative in brackets 5.4 meters per second squared over 2 times negative 9.81 meters per second squared. Putting that in our calculator and knowing that the negatives do cancel out, top and bottom, we get 1.486. Continuous which rounds to 2 sig figs is 1.5 meters. In the upwards direction, we got as a positive value. Let's do a quick assessment. Yes, we got a positive value, makes sense because we're achieving a positive height in the positive direction. We end up with meters, and how so? We got meters per second squared, all divided by meters per seconds squared, and this gives us meters squared over seconds squared divided by meters per second squared. The second squared cancels, one of the meter cancels out, leaving us with meters, units check out, of roughly 1.5 meters. So it's something that's doable. You can throw a rock that's 1.5 meters above where you are. And no, I didn't do something which I should have done earlier, which is reading the question carefully. This is the maximum height above the cliff, not above the ground, below the cliff, but this is above the cliff that the rock reaches. So when you're reading a problem, please read carefully. I could have easily asked for the maximum height above the ground on the bottom, and you would have to add the distance of the height of the cliff. So be careful of the question. Question B now. Final velocity of the rock before it hits the bottom of the cliff. Okay, so now we're interested in the bottom, when the rock reaches the bottom of the cliff. So that's going up, boop, 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 to the top, and then bam, coming all the way to the bottom. Again, I'm going to label the upwards direction to be positive. And as for labeling some of the values, we know I'm going to choose this point here for my initial point, and this point here is my final point of interest, because we are trying to find the final velocity of the rock right before it hits this bottom over here. We know at the initial point, the initial velocity is 5.4 meters per second. We know that gravity is always in effect and always negative 9.81 meters per second throughout the trip. We also know, we also don't know and want to find out this final velocity here. But most importantly, we also know the height of the cliff. This ball, you might be thinking, oh, do I need to add this distance here, this distance, and this distance as my total displacement? No, that's the distance. It's not the displacement. Displacement, you need to look at the difference where the ball was to where it finishes. It's the difference in position, and it's this one over here. This difference in position is actually the height of the cliff, which was, I believe, 32 meters. But is it just 32 meters? Aha, you might have seen I left a space here. You are right. The displacement is in the negative direction here, meaning it needs a negative sign. Haha, I bet some of you are going to forget that negative sign, and it's going to churn up a whole different number for you to work with. So something to be very careful of. Now let's go and identify the kinematics equation that we need to finish this off. We have U, A, V, S, again, A. So this equation is going to save our day. But this time we're solving for final velocity. Hey, that's a lot easier. I just need to put in everything in here, plus 2AS. And to isolate for the V, I just need to take the square root of everything. That leaves us with final velocity is equal to the square root of U squared plus 2S. Substituting everything in, we have 5.4 squared meters per second squared, plus 2 negative 9.81 meters per second squared times negative 32 meters. Now, if you had put this as a positive value instead, if you screwed up, this whole term here would be a negative value, so you end up subtracting this number, giving you a whole different number to take the square root of. So something to be very careful of. Let's put that in our calculator. That gives us 25.632 meters per second, and a few things to check off before we finish. First, we need to round this off to 2 sig figs, rounding up to 26 meters per second. But another thing is, when you take the square root, we are assuming we get a positive and a negative value because we're taking the square root. So, and the one that makes more physical sense is for our final velocity to be negative, since it points in the negative direction. So I'm going to put a negative sign in front. or I can say this is 26 meters per second downwards. Either way of communicating this to me or to anyone is acceptable. The language is more clear in some sense because if you write the negative sign, people have to refer back to your diagram or whatnot to see that. And I would do the same thing when I'm marking your papers. Let's do a quick check, assessment of our value. We end up with a negative sign. We checked that already. Let's check the units off. So in our first term, we have meters per seconds, and all of that is squared. The second part, we have meters per seconds squared times meters again. And all of this is square rooted. We are left with the square root of meters squared over seconds squared, plus meters times meters gives us meters squared divided by seconds squared. And when you add two things together, it's just the same thing. Apples plus apples just gives you more apples, right? Meters per seconds over seconds. The square root cancels out with these the squares, leaving us with meters per seconds, checking that one off as well. Okay, 26 as a value sounds relatively reasonable considering we have 5.4 initial velocities to start with. The ball does get to speed up and gets to speed up over the course of 32 meters. And we know as the ball reaches here, it's going to have a negative velocity of 5.4 meters per second based on the previous video, how your projectile motion is symmetrical. So as it's going down, it's going to gain more speed, 32 meters worth of speed as it's going down, giving us 26. It's reasonable, okay? It's reasonable, I would say, okay? Next up, we have C, the time it took the rock to reach the ground below. Okay, so we're talking about below the ground. We're below the cliff again, so exactly the same setup as last time. It reaches the ground, and I'm going to put that as labeling as my positive direction. We are trying to find the time in this question, not the final velocity, and meaning I'm going to label this part as my initial of my computer, this one as my final, meaning that my initial velocity I have is 5.4 meters per second from the continuation of the last problem. I want to know the time. I know the displacement is negative 32 meters, and we always have acceleration of negative 9.81 meters per second squared. There are actually two ways of solving this problem. There is an easier way, a shorter way, and a longer way. I am going to do both, and I am going to put some parts of this video in fast play, but of course I will still explain the majority of the work that I'm doing. The first part, I would say, is the easier out of the two, and that is using our final velocity here from the previous question, and I will write that down, which is negative, and I'm going to keep all my digits, 25.632 ... meters per second, saving that on my calculator, and I'm going to assume that I have the following here: my final velocity, acceleration, time, and initial velocity. These two, and if I look at my my four kinematics equations, I have the first one. V, U, A, and T is the one I want to find. So what I'm going to do, and since you've already seen me do this before, I am going to solve for T from that equation, and I'm going to use a different color here. I'm going to use this one here for my first solution. So first solution, I'm going to use V equals U plus AT. Okay, then I'm going to solve for T. And this is where I'm going to put myself on fast play. A few things first is that in this problem, you need to make sure that when you're substituting in your values that you do not forget to put in the negative sign, especially for the final velocity, subtracting the initial velocity, dividing by a negative acceleration here. So that your final answer ends up to be positive, okay? So that's one solution, and this assumes that you know the final velocity, which means that if I had not asked this previous question, you may not have that number to work with. So one of the ways of solving this is, if you didn't have question B to set you up, is you had to do question B yourself. If I just asked this question to you straight up. And now then after you have your final velocity, then you can do this step to solve for the time. So it becomes a two-part question, two-part solution problem for you. And that's something you can, I expect you to be able to do. And of course, we will continue to do more examples where two steps are involved instead of just the one. The next solution, which is I would say a little bit more, it's more mathy for sure. And you can look at my other videos on how to do this on a graphing calculator. But of course, let's see it first. And this one, it uses what the question gives us, this height of the cliff, the displacement there. And it's of course, if you're thinking about, well, I solved for this final velocity, what if I got this value wrong? It's better to use values that were given to me in the question, and you're absolutely correct. So if I had to just use all the values given to me from the question, then it's UTSA, and if I go to my 4 kinematics equations, that would be this guy over here, SUT and A, okay? So let's write that down. Now here's the problem. Now we have S, we have U, which is a positive value. It's not 0. We also have acceleration, but now we end up with two t's, our unknowns in two of the terms, and they are raised to different powers. And what we have here is what you know, or you may not know. We have a quadratic equation. If you've learned quadratics before, kudos. You're welcome to use that to solve this problem. And I can show you that way. And the other way is using and putting it on your graphing calculator and finding intersection point on a graph. That way if you can do it, that is great. But for most of us, I think we're more comfortable with going with our first solution. I will still go through the second solution. You're welcome to just stop the video here and just move on, or you're welcome to watch it in fast play, or you're welcome to just mumble it through and maybe learn something new. Damn, that rhymes. So let's try it the quadratic way. So what I'm going to do is I am going to actually put in my values first, so that you can see what the quadratic looks like. So here I have S, I have my displacement is negative 32 meters, so that's going to change my color. This is equal to U, which is 5.4, and I'm going to just not use the units here so we can just see the numbers, because it's already giving us a headache already, plus 1/2 AT squared. And don't forget acceleration is negative here, and then that's t squared. So for a quadratic, we need to rearrange it so that everything is on one side of the equation. I actually prefer to have this term over here that's beside the square, t squared, as a positive value. So I'm going to move that to the other side of the equation. So I'm going to move everything on one side. And so including this guy over here. So in fact, I'm going to actually need to subtract this. And because this is a negative term, I can make that a positive and subtracting this term instead. It's the same thing, right? But add a negative, same as me subtracting. So I'm going to also add this term here all to the other side of the equation. Okay, we are left with 1/2 9.81 t squared. And I'm going to bunch it up so that my t squared is my first term, and my singleton t is my second term, and my no t term is my third one. Minus 32 equals 0. Okay, so for my quadratic equation, you can pull it out. Imagine this coefficient here is my a term, this coefficient is b, this coefficient or that number, that term is c, so that my solution here, t is equal to minus b plus or minus square root of b squared minus 4ac all divided by 2a. That's something you'll learn in math later, or you have already. Good for you. I'm going to substitute all of these values into my quadratic, which I'm going to put here. So negative b, negative 5.4, plus minus square root of b squared, which is 5.4, and sure, there's a negative sign, but that's going to turn positive anyways, minus 4a, 1/2 times 9.81, not very clear there. Okay, some brackets to help us out. And c, which is negative 32. Okay, so the negative signs stay in there. They also jump in for the ride. 9.81. Okay, so I will now put this into my calculator for us to see what we get. Now here's the thing, I'm actually going to I want a time value that is positive, okay? So most likely I'm going to need the positive sign. So I'm going to add this square root here instead of subtracting it, because I'm more likely to get a positive value that way. But I'll try both and we will see what happens. So negative times a negative, I get positive 5.4. I'm going to add this big huge quadratic, and I know that a positive value is minus 4 times 1/2 times 9.81 and times negative 32. I'm actually going to break this off here and just press enter. Divided by 2 times divided by 2 divided by half. That's just cancel each other out anyways, but I get 3. Hey, I get 3.16. Hey, it's the same as we got before. So it works. 1/6 and that becomes 3.2 seconds, rounding up to 3.2 seconds. Okay, and then if I had subtracted, and we can see what happens here, minus square root of 5.4 squared, that just becomes positive. The negatives you square up negative sign, it becomes positive anyways. So notice that's going to give us a negative value to work with, and this negative value times divided by my bottom, which is still positive, is going to give us a negative time value, which doesn't make sense. So whenever you're in doubt, try both values, and the positive one always wins out. So that's our quadratic to work with, okay? So you could do it that way. If you want to see the graphing way, I can quickly show us, but for more detailed explanation, there's another video that I've made that talks about how to put complicated equations in your graphing calculator to do it that way. So I'm going to show you one way on your graphing calculator that can quickly do that, and that was from a different example. So here I have, these are my values for a graph. I'm going to graph it, and I'm going to find a point of intersection, which I'm able to do here. So here, let's put the graph down. So I'm going to do it this way. I'm going to put one side of my equation, which is just negative 32 on one side, on one of these y1s as one of the equations, the other one, I'm going to put this equation on the other side, something on the other side of my, and I'm going to use x instead of t. So that's the other side of my equation. So I have actually minus, I'm going to use this side, which is minus 1/2 times 9.81, which, and then my t I used as x squared, okay? So I got two equations, and I'm just going to quickly do a zoom fit to make sure all equations, both my lines, I can see both lines on my graph. Okay, notice the point of intersection here, past the origin in the positive section of the x-axis. That is the intersection point I want, so I'm going to go second calc, go down to intersection. I'm going to press enter. I'm going to move my cursor closer to the x side, and selecting my first curve, I press enter, selecting my second curve, which is the other line, and this, it just does something funny like guess or whatever. Ignore that. Hey, and the intersection happens exactly at x is equal to 3.1633, exactly what we got before. So that's the graphical way, and I'm just going to write that down. You can use graphing calculator to also get the same value, 3.16, giving us this at the end, okay? So which way do I recommend you to do, or which way do you prefer me to mark or whatever? The first solution is fine, okay? So meaning that if I didn't give you question B to kickstart you, you can do that whole step to find the final velocity and do it that way. Maybe it's a lot easier. If you want to do the quadratic way, make sure you show all your steps for sure. If you decide to use your graphing calculator, I would prefer you to write down your initial equation, how you substitute it in your equation, and maybe a note of how you use your graphing calculator. Use graphing calculator, find intersection point between this guy and this guy, or something like that, okay? And then showing your final value here and round it up, okay? So those are all possible solutions that that you can show me. If you've gone through all these videos and you watch them patiently, or even on fast play because you got things or whatnot, kudos, great job, keep it up, you're doing awesome. All right, if I don't see you for the last part, Fat Mama Physics signing out.